So this is a bit of astrology, is it?
That's not astrology.
Okay, right, okay.
Astrology is a banned topic.
Okay. So I've got some questions here about space that actually Sofia's going to work through. They get a bit tricky, but I think that's justified. These are from the Astro round 1, from part of like the whole British Physics Olympiad and the British Astronomy and Astrophysics Olympiad. What we're going to do, just a quick short question from part 1 of it. So you've got section 1, which is an hour long with the kind of shorter questions, and then section 2 has got, I think, 5 questions, and you choose 2 to do from that. So we'll do a couple of those questions, just to sort of show what's out there. So I say you're going to do all the work, because you're going to sort of, you know a lot more about this than I do. But okay, let's have a look. Maybe let's just go for
the first question.
First question. So question 1, part A.
So question 1, part A. That's 3 marks. So an asteroid in a circular orbit has a maximum angular separation from the Sun of 25 degrees as observed from Earth. What is its orbital period in days? I'm going to draw 2 diagrams actually, because what they haven't told us is whether the asteroid is nearer to the Sun than the Earth or further away. So we have the Sun in the center, and let's say that the asteroid is further away from the Sun.
Hold on, that is an amazing circle.
Let's say the asteroid.
Come on, that is a good freehand circle.
You're going to jinx the next one. The next one might not be as good. See, I told you the next one wouldn't be as good because you complimented the first one.
Okay, right. But that's good. That's good enough. Yeah.
Yeah,
okay.
It'll do. Let's say the asteroid is closer to the Sun than the Earth, and here let's say the asteroid is further away from the Sun than the Earth. Now think about the question. So its maximum angular separation from the Sun is 25 degrees as observed from Earth. That means that if you're stood on Earth and you look into the sky, you look at the Sun, you look at the asteroid, you go like this, that's 25 degrees when the asteroid is at its maximum separation. So the biggest possible angle you're going to get is 25 degrees. But if the asteroid is further away from the Sun than the Earth, then the maximum separation is going to be 180 degrees. So that's not the case.
Yeah.
Just thought I'd clarify that. Okay, we know that it goes Sun, asteroid, Earth, but where exactly is the asteroid when it's at its maximum separation from the Sun? And more importantly, like, why would we need to know this? What can we extract from this? So we're asked for its orbital period in days. And in the back of my mind, I'm thinking, I know Kepler's law, which relates the orbital period of an object to its orbital radius. So, that might be useful. We might need to use Kepler's third law for this.
And I think everybody knows that doing A-level physics, that it's, t squared is proportional to r cubed. And so, yeah, that's the kind of thing that anybody doing A-level physics should, especially by the end of year 13, have a good idea about. So that could be important,
Yep. And that equation is given in the formula book, but we'll come back to that. Okay. We're just keeping in the back of our minds right now that if we can find the orbital radius of this asteroid, then we can find the period from that. And that's very good.
Yep.
So to find the orbital radius, I mean, we've been given a geometrical piece of information. So let's see if we can extract its orbital radius from that. I'm going to draw another diagram. So let's have a think about this. I might use a pen. Let's say the Earth is here.
Yep.
Where is the asteroid when it's at its maximum separation? And you kind of do this for a bit. And this is quite difficult to explain because you kind of have to, geometry, like the way people understand geometrical things is like kind of personal, like it's kind of difficult to put it into words. But if you kind of do this for a bit, you can convince yourself that the asteroid will be at its maximum separation from the Sun when the line joining the Earth to the asteroid is tangential to the asteroid's orbit of the Sun.
That makes sense to me. I'm almost sort of like, I can't believe it's like you kind of visualise kind of lines and you think, okay, well, this is going to be...
Exactly.
Yeah. Okay, that's really badly explained, but it's like in my head I know what's going on. Yeah.
I guess it's because you can't get, your angular separation can't get any bigger than tangential, therefore it must be the maximum. So let's draw that on without a ruler. That was quite bold.
That's good.
So let's say the asteroid is here.
Yeah.
It's at its maximum separation. Let's call the maximum separation theta. I'm usually reluctant to label angles and numbers on my diagrams. I usually label symbols and then write this at the side. And that way, it's when I do my calculations and manipulate anything symbolically, it's clear what symbol means what. And then the people marking it are less likely to get confused, and so you're likely to get more marks.
Yeah, very good.
Okay, so we know this, and let's draw on this line. And it's like way a triangle.
And it must be a right angle triangle, because here you've got the radius of the circle to a tangent. So yeah, 90 degrees.
Yes. In green, because why not? Let's label some more things. I'm going to denote the orbital radius. By the way, we're assuming everything has a circular orbit.
Yeah.
It doesn't explicitly say that the Earth has a circular orbit, but we usually assume that it is. So let's call the radius of the asteroid's orbit R subscript A, and the radius of the Earth's orbit R subscript Earth symbol, which, by the way, we mentioned in the previous video, but that circle with a cross in it means Earth in general astronomy notation.
Yeah.
Cool. Is there anything else we can label? I don't think so, but I think we've got all the information we need. So I've drawn this triangle in context. Let's just take the triangle out of context so we can focus on it a bit better and sort of imagine it more easily. Okay, so we've drawn out this triangle again, and so we're looking for the orbital period in days, and as we mentioned, knowing RA, the radius of orbit of the asteroid, is going to be really helpful in finding the orbital period. So let's go ahead and find RA. That's trigonometry, SOHCAHTOA, all the fun stuff.
Yeah.
So we have sine theta equals radius of the asteroid over radius of the Earth. So you get that the radius of the asteroid is the radius of the Earth times sine theta. We won't substitute in our values yet, we'll keep it symbolic for now. And as we mentioned, we have the radius of the asteroid now in terms of quantities that we know. So that's amazing, because we can now use Kepler's third law to find the orbital period in days. And you don't need to memorize that. It's given on the important formulae page at the beginning of the paper. As we mentioned in the previous video, definitely have a look through this list of important formulae and just make sure you know when and how to use each one, what each symbol means and when you should get that formula out.
And I think it's interesting here that they're using A to represent the radius rather than R. So, you know, you should realise that that's something that you might be used to seeing, but they're just using different terminology for different things. So they're using an A rather than R, but that's just a convention in astronomy, isn't it?
Yeah, I'm using R here because I know that these orbits are circular, or at least that we're approximating them as circular. And so describing it as the radius would be standard.
Yep.
However, Kepler's third law doesn't just apply for circular orbits, it also applies for elliptical orbits.
Yep.
And A is the standard notation for the semi-major axis of an ellipse,
which
is
as well.
This length here.
Yes.
Yeah.
That's cool. Okay, so we've got some information there. We know there's a relationship between t squared and r cubed, I guess. And so I guess we can use that for the next step, can't we?
I always like to write down the equations I'm using before substituting things in. That way, everything you're thinking is so clear. Okay, so we want the orbital period. So if we just square root that. Okay, we know all these things. I mean, here we have A equals RA. Again, those are just two different symbols, sorry for the confusion.
Yep.
Let's substitute in those values. So here we have RA, and that's radius of the Earth times sine theta. You know, I'm going to write that out again. It's super clear. Okay, that's 1.5 times 10 to the 11.
So that's again given to us in the table, so just one astronomical unit.
Yeah. Don't forget to cube things. But it's not the mass of the Earth that we want here. Be super clear.
Oh, okay, so it's the mass of the sun, isn't it?
Mass of the sun.
Yeah.
If you have just M, use subscripts or any other method to make sure that you're following what it is you've got. Mass of the sun, 1.99 times 10 to the 30 kilograms. And if we slap that into our calculator, we get something like 8704617 point something seconds.
Okay, so that's come out in SI units.
Yep, and this is exactly how my calculator gave it.
But we need to know that period in days.
Yes, we want to know it in days. So let's just go ahead in days. We want to divide it by the number of seconds in a day, which is 60 times 60 times 24. And we get 101 days.
And I guess that's kind of what you'd expect. It's closer to the sun than the Earth, so it's going to have a shorter period of rotation.
Yes, but we actually didn't really need to use this formula. We could have done this much quicker. It's always important to make, if not a physical note, then definitely a mental note of what units you're using. Because if we use T in years and A in astronomical units, and the mass that we're orbiting around is the mass of the sun, then the version of Kepler's third law that we can use is simply T squared equals A cubed.
Okay.
Yep.
I didn't know that. So that's like a super, so it's not just proportional, it's an equals.
Yes.
That's awesome.
If the period is in years
Yeah.
and A is in astronomical units, because if you think about it, the Earth's period is 1 year and its distance from the sun is one astronomical unit.
Yeah.
So you have 1 equals 1.
That makes sense.
And we can do a similar thing here. But that way we're going to get its orbital period in years. So we just need to keep that in mind. So T equals square root of A cubed. So let's just do that. That's equal to, but we need to do it in astronomical units. So the radius of the Earth's orbit is 1 astronomical unit. So we get 1 times sine theta. So we simply get sine 25 degrees to the power of 3 over 2. And you get 0.2747, blah, blah, blah.
And that's of a year then, is it?
in years. And so by multiplying that by the number of days in a year, which is 365.25, you get 100, which is essentially the same answer as what we got before, but just via a quicker method. It's just a quicker version of Kepler's third law.
So they're slightly different. Is that maybe just due to the constants?
It's due to the constants. Yeah, it's a very small difference.
But I think that's I haven't seen that one before actually, and I didn't realise that. So that's brilliant.
Yeah.
So yeah, fantastic. So again, there's like lots of different ways to approach the same question. I suspect in the Olympiad you wouldn't necessarily write out this first one.
Yeah, I just wanted to sort of throw that in there just to make sure we were on the same page about why. Because if I immediately drew this, it'd be like, why have we put it there? But yeah, that's just a quick one.
So actually, that's a really nice question, I think. So that's kind of the kind of thing you might see in part 1. But of course, now we're going to go on to part 2. So this is section 2. We're going to do question 3. Again, this is something I didn't know a lot about beforehand about Jean's mass, but I think it's a lovely question actually.
Yeah.
So how would you approach it?
So, well, first you've got to read the question.
Yeah.
So, what is the Jean's mass? The Jean's mass is defined as the mass that a spherical cloud of interstellar gas must have to contract under its own weight. How heavy does a cloud have to be to collapse and contract?
Okay, cool. And I guess that's important for like stars forming, and then you get this kind of nebula, and then it's like protostar and all of that stuff that again a lot of people might have done at GCSE, but at GCSE you never really do many equations. It's just like stars form and then they die and things. So, okay.
Yeah. We're answering a very interesting question because sometimes you get nebulae that just sit there and vibe. You just have a huge nebula, and then sometimes you get ones that become stars. And the question is, well, what's the difference, really?
Okay.
The difference is in these quantities, like the Jean's mass, Jean's radius. Those things refer to sort of the limiting case between having just a vibing nebula and like a collapsing nebula.
Okay, so some scientific terminology there, like
like
cool.
vibing.
Yeah, vibing. Okay, cool. So the first one then, so we've got something about uniform density, mass m, radius r. The first one is to show that its gravitational potential energy is EP is equal or equal to minus alpha gm squared over r. So that one there's a lot of work for 7 marks, isn't there?
Yeah. So here they're saying show that the total gravitational potential energy is this. Really, they're just saying find the gravitational potential energy and then compare it to this, and hence find alpha.
Cool.
So the method we're about to do, if you haven't really done questions similar to this before, it can seem quite shocking, kind of like, how would you know to do that, like straight away? But eventually it becomes kind of standard, and it really builds on differential equations from A-level maths and that kind of thing. Yeah.
And I think this is why it's nice, because a lot of the time in A-level physics, you don't do any integration, differentiation. It's just relatively straightforward maths. But I think this one is nice because it shows how maths is so important to understand the physics and then what you're going to be doing at university and so on.
Yeah, this is definitely it's serious maths in the context of A-level, but very much with that physical intuition behind it as well.
Yeah.
Which, again, makes it slightly like wow at first, but then once you've done one question like this, it very quickly, you begin to spot the pattern, and when you get a question similar to this again, you kind of have an idea of what to do. So we are going to draw our star of uniform density. We want to know what its total gravitational potential energy is. Okay, let's think about gravitational potential energy. At A level, gravitational potential energy is minus g m over r. So we've got g, the mass of the attracting thing, the mass of the thing that's being gravitationally attractive, and the distance between them. And it's not immediately clear how we're going to put this in the context of a spherical star, where you haven't just got one thing attracting one other thing.
Yeah.
You've got an entire star attracting itself, essentially.
Yeah, okay, I see this, yeah.
That's what makes this a bit more complicated. We haven't just got 2-point masses at some distance. You've got to get a bit creative with this. What if we tried to apply this formula in a specific way that would allow us to then sort of sum up the gravitational potential energy of the star?
Okay.
Again, this might seem like a bit of a leap, but once you know this method, you'll begin to see other places where you can apply it.
Yeah.
So we're going to split up the star into spherical shells. So imagine like you've got, just
like an onion or something.
Yeah, like the layers of an onion, yeah, pretty much.
Like a big space onion.
Yes. And I'm going to draw one such shell here.
Yeah.
I've drawn this very thick, but imagine this is extremely thin in the context of the star.
Okay.
Let's say that our star has radius r, as the question has said. If anything, I would go ahead and when I read the question, I should have done this straight away, which is what I would usually do. But when I read the question, I go through and I immediately write down things like this, because then you're making sure that you're using the correct symbols that are consistent with what the question has told you without having to constantly sort of read back over it. Okay, so let's say the star has radius r, and it has mass m and density rho. And let's consider a shell. And let's say that this shell has such a thin thickness that we're going to call it dr, kind of like dx when you're integrating.
Okay, so the d just means it's kind of approaching zero, that thickness. So
just
it's not like
dr.
a delta, which is like a change in r. It's like dr, it's like even smaller.
The smallest possible change in the radius that you can imagine.
Yeah.
That's the thickness of the spherical shell.
Okay.
And the distance of that spherical shell from the center is small r. And we need small r to have a different symbol to big R, and you'll see why that is.
Okay.
Again, seems a bit rogue, but it's going to make sense. It's going to make sense. And now we're going to say, what is the gravitational potential energy of this shell? Well, it's going to be infinitesimally small compared to the gravitational potential energy of all the shells when you add them together, right?
Yeah.
So we're going to call it DEP.
Okay.
So what is DEP? Well, we have a look at this formula that we know from A level. It's going to be minus g times the mass that is attracting that spherical shell times the mass of the spherical shell over the distance of that spherical shell from the attracting mass. And it gets a bit goofy here. So we have our minus g, but what's the mass that's attracting the spherical shell? It's actually the entire mass enclosed inside of it that is big M.
Yes.
Does that kind of make sense?
It does. I was looking for a highlighter to kind of sort of colour it in, but basically that's all of the mass contained within that shell.
Yes.
And that's all going to be attracting everything outside of it. So yeah.
You may think, hey, but it's not all in the centre, it's kind of spread out. But we'll come back to that in a second once we've finished writing this down.
Okay.
So we're going to write Gm enclosed, to denote enclosed mass
Yeah.
by the shell. And then the mass of the shell. What symbol are we going to use to denote the mass of the shell, considering it has thickness dr and gravitational potential energy dep? Its mass is also going to be infinitesimally small, right?
Yeah.
So should we call it dm?
Yeah, let's do that.
And then the distance of that spherical shell from the attracting mass is the distance from the center. And again, we'll come back to this. So that's going to be small r.
Yeah.
Okay, now question. Why is it that we can consider all of the mass inside as if it were all in the center?
Do I have to answer that, do I?
Yep.
Simply like the centre of mass is in the centre, maybe? Is that like a simplistic way of thinking about it?
Yeah. For example, when you're standing on the Earth, if you were to compactify the entirety of Earth's mass into one point, that would have the same gravitational effect on you as the Earth in its current size.
Yeah.
In the same way, the mass enclosed by this shell has the same gravitational effect on that thin shell as it would if all of that mass were compactified into the center of the star. If you think about it, it makes sense intuitively. There are also mathematical ways to prove this, but most importantly, just get an intuitive sense for it.
Cool.
Yeah.
Okay, so let's move on. So how do we work out the total mass of what's enclosed by that shell?
Yeah, so the total mass of what's enclosed by that shell, well, we know the radius, and we can work out the volume of the shell using the radius of the shell. So let's do that. So that's the mass enclosed. That's the volume of the shell, the volume enclosed by the shell, and the density of the star.
Yeah.
The next question is, what's dm? What we want to eventually do is integrate both sides of this expression, which again might seem a bit rogue if you haven't seen a question like this before.
Yeah.
But it becomes kind of a standard procedure that you do once you see a few of these questions.
Yeah.
That you consider a thin slice of something, and then you do an integral on both sides, and you're like summing over all these thin slices. And yeah, I think this is one of the main ways that sort of calculus, like all the integration things, they come into physics.
Yeah.
Questions like this really kind of bring that out.
And I think when you've got something like a dr there, you think, okay, that's a clue, there's going to be some kind of integration going on potentially. Okay, so what next? What's the next stage?
So we know that r, to sum over all of these thin shells, we know that small r can go from 0 to big R.
Yeah.
So we probably want to integrate over R.
Yeah.
So we want to write dm in terms of R, because writing dm isn't that useful to us. So let's write out what dm is. In the same way that the enclosed mass is the enclosed volume times the density, this infinitesimal mass is going to be the volume of each shell multiplied by the density. And the volume of each shell, because each shell is so thin, you can approximate its volume as simply the surface area of the shell multiplied by its thickness. If you imagine spreading it out.
Yeah. So I'm kind of thinking of like that kind of shell bit, or the skin you get on an onion is like super thin, almost like paper thin, compared to like the thickness of like the onion itself. So yeah, if you wanted to work out the mass of that, it's a bit like looking at the surface area of that onion. I probably should have known to describe this. Maybe this analogy is not going to work completely, but
no, I think it will.
If you knew the thickness of the onion skin and you knew the area of the onion skin, you could then work out the mass of that onion skin, couldn't you?
So
that's kind of what we're saying, isn't it?
The area is 4 pi r squared, is rho, and we multiply by its thickness, dr.
Cool.
Okay, let's substitute all of these shenanigans into there.
Yeah.
This is going to take a little bit of simplifying. It's also worth noting that in this final expression, they want it in terms of the mass and radius.
Okay.
But here we have it in terms of the density and radius.
Yeah.
So we're going to keep in mind that we will eventually want to convert from it being in terms of the radius to it being in terms of the mass.
Yeah.
But for now, we'll just simplify that. Yeah, I've just done this in one step here, but please take as many steps as you need. We've done this to save time and space.
Yeah.
But yes, take as many steps as you need to simplify anything. It's better to write too much than too little.
Yeah.
Okay, so that's dp. We want to, if we integrate both sides, like so. So if you integrate this, then this is what you get.
And that's because you've gone from r to the 4, you've gone up to r to the 5 divided by 5, and you've got a 3 over there, so that's why it's a 15. Cool.
Again, we won't write out every single step just to save space and time, but yeah, do work through these steps if you're unsure of any of them.
Yeah.
But here we have simply integrated both sides of the expression. But then we look back at the question and we're like, that's not like what they wanted.
No.
And the reason for that is because they wanted it in terms of mass, not density. So let's just go ahead and do that. So let's substitute in this expression for the density back in here to get the expression in terms of what they wanted.
Okay, I can see where this is going, but it seems to be, again, a lot of writing.
Yeah.
And I think sometimes there's no there's no point doing shortcuts because then you're going to miss out.
Yeah, you will probably need to do more writing than this. I think when actually working it out for myself, I would do more writing than this to make sure I've got all the steps correctly. And so we've substituted that in. And again, to save everyone's time, we're going to simplify this in one go. You get the 3 cancelling with the 3 there, 4 cancelling there.
When you're watching somebody else do the maths, it's so nice because you can really think about it. You can like be one step ahead, can't you, as you're actually writing it down. So yeah, so you've got 3/5, and then you've got m squared, which is the m squared over here. You've got r to the 6, but you've got r to the 5 divided by r to the 6, so that's 1/r.
Please don't do this in your head. Please just write it out fully. We're simply doing this to save time and paper for now. So eventually when you simplify this, it comes out to be minus 3/5 gm squared over r. Glancing back at the question to see what exact form we should give our answer in, they said where alpha is a rational constant to be determined. And so we have a look and it says minus alpha times gm squared over r. So alpha is 3/5.
Perfect.
Hooray.
Very good. And I think, again, it might be, if you've never done anything like this before, this seemed like a, where do you begin?
Yeah.
But I think that this kind of approach, especially where you're maybe thinking about the shells or like a thin part and then you're integrating to look at the whole thing, I think is something that once you've done it a couple of times, you might see it in many other bits of physics or just the way that you approach problems. So I think it's a really elegant solution.
Yeah, definitely. I'd say questions like this are actually very relevant to the kinds of things that the UK team cover in their training for the International Olympiad. They too need to know things like Jean's mass, just have the derivations kind of like ready to go.
Yeah.
So yeah.
Brilliant. Right, should we do part B?
Yes. So part B, but a bit of preamble for part B. The virial theorem states that for a stable system bound by conservative force, the kinetic energy is equal to -1/2 times the potential energy. This is probably going to be useful considering it's in the preamble for part B.
Yeah.
But let's park that for now. Let's write it down actually.
So again, I think a lot of this will be familiar to lots of students. You know, you've got kinetic, potential energies, the time average kinetic and potential energies of the system respectively. Yeah, so far it looks okay.
Yeah. I mean, the virial theorem might not be something that you've ever seen before, but they've told you what it is. Again, of course, like when you're learning physics and astrophysics, you want to understand where everything comes from. But when you're in the process of doing an Olympiad paper, you they give you an equation, you're like, okay, let's go, kind of thing.
Yeah.
So yeah, again, I think I said this in the previous video, but don't worry if they give you something and you're kind of like, I don't really understand why that's true or completely what that is.
Yeah.
The point is that it's introducing you to new concepts quickly and seeing whether you can apply them just as quickly. And then you can always sort of do some Googling and figure out why that's true and the derivation for this afterwards.
I must say, as a bit of an aside, the actual mark schemes that you can download on the website,
they're very good.
They don't just have the answer, but they've actually got work solutions. I think these ones have been done by Alex.
I think they have been done by Alex,
the legendary Alex.
He's awesome.
So yeah, so lots of colour, and it kind of sort of shows like alternative answers, different approaches. So it's not just the answer. It's actually kind of a brief set of really detailed, thorough work solutions. So yeah, I think if you get stuck, these are a godsend when it comes to actually practicing these papers.
Yeah, definitely check them out. It's how I checked my answers. So.
Yes. Okay.
All right, so part B, consider a nebula with uniform density ρ and uniform temperature T. So let's just write those things down. These are the things that we know. Derive an expression for the Jean's mass purely as a function of these two variables and various constants. Assume the nebula to be spherical and composed only of hydrogen atoms of mass NH. So we know that the mass of each particle is going to be mh, because that's what they've told you to assume. And yes, they've also helpfully told you what value to use for alpha if you didn't get one in part A, but we have got the correct value of alpha in part A, so we're going to use that.
And I guess, again, that's a clue that if you know the value of alpha, you're going to have to use this equation up here. So
yeah, this is true.
Again, it's another bit of like, it's giving you EP here, that's what EP is, so that's going to be used at some point, I'm sure, in your answer.
Okay, cool. And you might read that and think, hang on, what was the gene's mass again? You go back to the preamble at the beginning of the question, and it's the limiting case mass in between a nebula just existing and a nebula collapsing under its own weight. They've also given the virial theorem, which applies to a stable system bound by conservative force. Seems like it's pretty relevant. And again, that keyword stable implies that it's kind of like a border case, and which is exactly what we want when looking for the gene's mass. So let's see what happens when we simply apply this equation for the virial theorem that we've been given. Well, this is a spherical cloud, and we've actually just worked out what the potential energy of a spherical cloud is, right?
Yeah.
Except it wasn't really a cloud, it was a star. But it doesn't really matter what it is, because it doesn't sort of explicitly mean it's a star. It's just the potential energy of a sphere with mass m and radius r. So we can use that for whatever other context we want.
Yeah, and it's uniform density. So it could be a highly dense thing like a star, or something which is less dense like that cloud. So yeah.
As long as the density is uniform, we can use this as the gravitational potential energy of our sphere. So we know what to substitute in for EP, but what about EK? From A-level physics, we know that the kinetic energy of a particle in a gas at some energy is 3/2 kT.
And that's the average kinetic energy of each particle, isn't it?
Yes, that's
Cool.
the average kinetic energy of each particle.
Yeah.
So let's say we have capital N number of particles.
Yeah.
Which means that the total kinetic energy of this thing, of this entire cloud, is going to be 3/2 nkt. By the way, K here is Boltzmann's constant.
Can you remember that off the top of your head? Because a lot of these constants I use all the time, and then it's like, when you put under pressure...
1.38 times 10 to the minus 23?
Yeah.
Is it that?
Yeah, of course it is, yeah. So you knew that, yeah. Okay, but it's like, when you put it under pressure, like, do I know that?
Yeah,
is
yeah,
it like
no, it's because I was under pressure. I didn't.
Yeah, okay, right. So yeah, so again, just normal standard constants. And again, if you're not sure, they are given to you. So I think over here, do they have it?
Yeah, you guys don't have to remember any constants. They're all in this table here.
But they call it KB to show it's Boltzmann's
Yeah,
constant.
so Boltzmann's constant, you can write it as K, you can write it as KB, but I'm just writing it as K for speed, but
Cool.
they're exactly the same thing.
Yeah, perfect.
So let's see what happens if we just substitute in the kinetic energy, and from earlier we found that the potential energy was equal to minus 3/5 gm squared over r. I realise I've kind of written things in a column over here.
That's
I think
fine.
I might just continue
we'll
down
move
here.
to the left, shall we? Or are you going to keep going in the...
I think I might just continue down here.
Cool, okay.
Okay, so let's just substitute those things into the virial theorem. Okay, and simplifying that, 3's are going to cancel, 2's will cancel. Again, write out more steps if you need to. We're just doing multiple steps in one go to save time and space. The question's asked us to derive an expression for the gene's mass purely as a function of the density and temperature. Currently we have things like the total number of molecules and the radius of the cloud. So we got to figure this out somehow to make sure that it's not got the radius of the cloud, total number of molecules. We want this to be a function only of the density and the temperature and various constants, things like the Boltzmann constant, that kind of thing. So let's have a think about how we can do that. So here we have n, which is the total number of molecules, but we can write that in terms of the total mass of the cloud and the mass of each molecule. So let's just do that at the side here. We know that n is the total mass of the cloud divided by the mass of each molecule. And mh is a constant that we know. And m is the gene's mass, so that's the thing we're trying to find. So this is good, this is all legal.
Yeah.
What about the radius of the cloud? Well, we can write that in terms of the density and the mass, right? And then the density is one of the things that we want to get this gene's mass as a function of, and then the mass is the gene's mass itself.
Yeah.
So Here we'll also do, so we know that the density is the mass over the volume, which if you substitute in the volume of a sphere, you get this. Then rearranging gives you that the radius is. So yeah, here we have the radius in terms of the mass and density, and n in terms of the mass and mass of hydrogen. So this is fine. We can substitute these things in, and then we've got an expression that only contains the variables and the constants that we want it to contain. And this looks a bit goofy, but that's okay.
Yeah, it does look a bit messy at the moment.
Don't worry if your expressions look really messy. I think sometimes if you get like a really messy expression at like A-level or GCSE, it kind of means you've done something wrong. But that's not the case at Olympiads. Your expressions might look a bit messy,
Cool.
and that's okay. You just persevere. We want mass to be the subject of this expression, so let's rearrange. I will save the intermediate steps for you to do in your own time. But if you manipulate this algebraically and rearrange, you eventually get this expression for the gene's mass.
So I would say that, yeah, there's loads of different ways you could do this. I think if you've got to this point already, then you know that you can like cube sides or whatever it might be, you know, to kind of bring all the m terms together, and then you can, you know, again, neaten everything up. But I guess there's probably different ways that you could represent that.
Yeah.
But it's a case of going from here to there. It's not that bad. It's just sometimes a little bit time consuming, isn't it?
Going from here to here can be incredibly frustrating if you don't allow yourself to write all the steps that you need in order to avoid making small errors, because if you try and rush it, then it's so easy to make small mistakes. It's something I've definitely done before. So if you're not getting this final expression and you're trying to work through it, it's okay. Just backtrack and just try and do it in smaller and smaller steps. But yeah, that comes from just rearranging this expression here.
And in terms of answering the question, we've got the temperature T, we've got the density rho, and we've got the mass, which is a constant of mh. And that's what you've done there. You've derived an expression for the gene's mass purely as a function of these two variables and some constants.
Yeah. So most of this question was just doing some algebra after you substitute those things in. The conceptual leap for this question was knowing what to do in terms of substituting in the kinetic energy of the cloud and the potential energy of the cloud into the virial theorem, and also recalling that the kinetic energy is going to be 3/2 nkt, which hopefully most people will have covered in A-level. But if you find bits and pieces when doing these that you think, oh, maybe you're going to cover that in A-level, but you haven't yet, then it is worth just reading ahead, and if anything, it'll help you in your lessons.
Yeah, and also I think having the confidence that maybe when you get to this step, that you have the confidence to kind of keep going, because not everything comes out to like a nice little formula like you might have in the data book.
Yeah.
They can look messy and awkward, but there's not always this perfect thing where everything cancels perfectly. But I think it's that confidence that you've done the right thing so far, and then you keep going just with the kind of the information you've got at hand.
Yeah, I mean, if this formula was like easy to derive, they wouldn't have felt the need to name it after Sir James Jeans.
Yeah, exactly.
So
Okay, so we've done the first two parts, and now it's on to part C.
The current estimate for the average baryonic matter density of the universe is that it is equivalent to 1 hydrogen atom per 4 cubic meters. Can you imagine that?
So we're,
Like 1 atom per 4 cubic meters.
and that's the average density of the universe.
Of the universe.
Bearing in mind, some places have got a lot of matter in a small space, if you think about stars and us and everything like that. Okay, so that's incredible.
Consider a spherical region within the universe of uniform density equal to this average, and uniform temperature equal to that of the cosmic microwave background, and composed only of hydrogen atoms. Find the radius of this region such that it will collapse under its own weight in this very simple model, giving your answer in kiloparsecs. You are given the observed spectrum of the cosmic microwave background in figure 1. There's a few parts to this.
Yeah, I can see.
There are a few moving parts to this, but that's okay.
But I can see that there's a lot of information there. Some of it is actually interesting, like really interesting, I think, to kind of get your head around. I can obviously see how this relates back to the other bits, because we're looking at, is it like, you know, how big, what's the radius of this region, which I guess is going to link back to the previous work we've done. But there's also a graph here. So what would be your first step in this one?
My first step would be to go, hang on, what's going on here?
Yeah.
Because that's just a block of text right now. What are they asking us to do? They said find the radius of this region such that it will collapse under its own weight. Yeah, so my usual first step would be to go through and extract the values that are relevant. Here there's one value that's immediately given, which is the average density of the universe is equivalent to 1 hydrogen atom per 4 cubic meters. I'm going to use lowercase n to denote number density, i.e. how many particles you have per unit volume.
Okay.
So n average is, well, if you've got 1 hydrogen atom per 4 cubic meters, that's 0.25 things per cubic meter.
Yeah.
Okay, well, we've written that down. We've done my standard first step. Now let's have a look at what the instruction is, what we're being asked to do. So, find the radius of this region such that it will collapse under its own weight. Well, that's it's kind of giving Jean's radius. It's like Jean's mass, but it's the radius. So it seems like the expression for Jean's mass that we derived in the previous section is going to be very useful here.
Do we have that somewhere?
Yes, I've got it.
Cool, okay, so good, because I can't remember that off the top of my head, but we definitely previously worked out from part B Jean's mass.
I'm writing down MH and I'm thinking, hang on, are we still dealing with just hydrogen atoms? The answer is yes.
Yeah.
Okay, so we know that this is the mass at which a spherical region will collapse under its own weight.
Mm-hmm.
But we want to know the radius at which a spherical mass will collapse under its own weight.
Yeah.
But we can convert this.
Mm-hmm.
So how do we convert mass to radius? Well, we go via the density because we know what the density is.
Yeah.
So let's just go ahead and see if we can change this from mass equals something in terms of density to radius equals something in terms of density.
Yeah.
So as we know, the density is the mass over the volume. I feel like this is the third time I've written this down in this question. Density is mass over volume.
Again, it's a simple GCSE, like, you know, it's not just a case of looking at the volume or the mass or density of like small wooden blocks floating in water, but that equation comes up so often, doesn't it?
So we know that the Jean's mass, rearranging this, the Jean's mass, again, do the rearranging in multiple steps. We're just doing it for speed.
Yeah.
We know that the Jean's mass is going to be this. From rearranging the equation for density in terms of the radius and the mass of a spherical region, we know that the Jean's mass is going to be 4 pi rho over 3 times the Jean's radius cubed. And so if we just substitute this into there, then we don't need to worry about what the mass of this entire spherical region is,
Okay.
which is great because part C hasn't given us any information about the mass of that spherical region, nor does it care what the mass of it is. So let's just go ahead and substitute that. And we've been asked to find the radius of the region, so we want to rearrange for the radius to be the subject. We've got this expression for the Jean's radius right now.
Yeah.
We've been asked to sort of actually find the radius, i.e. we want to put numerical values into this, we want to find that radius.
Mm-hmm.
But do we even know everything that we need to put in, is the question.
That's the big question,
This is
isn't
where
it?
the kind of moving parts of this question begin. We've got the overall aim. The ultimate goal is to put things into this formula and get our J.
Yeah.
But we need to figure that out first. 15K, that K is a constant, big G is a constant, MH is also on the constants sheet. So the things we don't know right now are rho and T. These are the things that we need to focus on finding right now.
Okay.
Okay, so let's find T first. Either from bits and pieces from A-level physics or from looking at the syllabus documents or self-study guides on the BFO website, you'll know that we can link together the temperature of an object with its peak wavelength. Here I've written out Wien's displacement law exactly as it's given in the important formulae page of the paper. I would usually denote this constant as B, so this is just how I would write it. It doesn't really matter how you write it, this is just how I'm used to using it.
Yeah.
And you may think, bless you,
Okay.
and you may think, oh, they haven't told us what that constant is. But they have, it's in the constants page.
Okay, so over here then,
Yes.
so on a different part of it.
So from constants sheet, we have that B equals, again, I just use the letter B to denote it, but it's fine if you don't do that.
Well, that's meter Kelvin, isn't it? Not millikelvin.
Yes, that can be confusing. Meter Kelvin. But then if you look at this, temperature is in Kelvin, wavelength is in meters, so
Makes
the
sense.
units of B would be meter Kelvin.
Yeah.
So we know that if we know the peak wavelength of the cosmic microwave background, we can plug that into this formula to find the temperature of the cosmic microwave background, which is what we're going to need to put into this formula.
Yeah.
And how are we going to find the peak wavelength of the cosmic microwave background? Well, we've been given a handy graph that we have to read something from. So let's go ahead and do that.
I've got a ruler here, so that
Yeah.
might help.
What we want to do is find what the peak wavelength is. Make sure you're always looking at what units are specified on the axes of graphs like this that you're given. It's so easy to accidentally miss that.
Yep.
Our peak wavelength here is given in centimeters, and in order to plug that into Wien's displacement law, we're going to need that in meters, which is that times 10 to the minus 2 meters. T is going to be B over lambda peak. One of the reasons why I went ahead and put the numerical values into this was because from just various popular science, I know that the temperature of the cosmic microwave background is 2 point something Kelvin.
Yeah.
It's good to have a gut check. If you have any idea what the value should be, it's good to just sort of test your answer against what that value is. And yeah, this is in fact 2 point something Kelvin, which is what I was expecting.
Yeah, good.
Awesome. And now we need to find rho. We've been told that the average number density of this cloud is 0.25 hydrogen atoms per meter cubed. We know we have n average hydrogen atoms per meter cubed.
Yeah.
And just multiplying that by the mass of each one will give us this. Okay, so now we have T in terms of things that we know,
Yeah.
and rho in terms of things that we know. So let's just go ahead and plug those into that formula. It's always a good idea to write out your entire symbolic final equation that you want before putting in numbers, because if you try to simultaneously substitute things and then also put numbers in, whenever you skip steps, it just makes it 10 times more likely that you might make a small mistake, which not what anyone wants. So after we substitute all of that in, we get, and this is in meters. If it's times 10 to the 20 meters, you probably don't want to give your final answer in meters, because times 10 to the 20, like numbers that big, they don't really mean that much to anyone. So it's much more meaningful to put it in a unit that kind of better reflects what kind of distances you're dealing with.
And it says here about using kiloparsecs.
Mm-hmm.
So I guess we could have used light years, I guess, at a distance like this, but I guess they've asked us to use kiloparsecs. And again, the parsec is given to you in the constants sheet, and obviously the kiloparsec is just going to be 1,000 times bigger than that.
Yes.
So the last step is like the simplest bit, isn't it?
Yep. In kiloparsecs, we want to take that answer in meters and divide it by the number of meters in the parsec. Well, the number of meters in a kiloparsec will be 1,000 times as much. And eventually we get this.
So 32.0 kiloparsecs.
Yeah, it's quite big.
It is. Again, I think these numbers are so big.
Yeah.
It's like, is that reasonable? Is that like massive? But it's like so hard to imagine, 10 to the 20 meters. But that sounds right. If it's the average density is so low, you're going to need a massive volume of space to actually have enough mass to then, I guess, kind of collapse under its own weight.
Yeah, it can be difficult to gut check these things when you don't really have a gut instinct already prepared for how large a bit of the average density of universe has to be to collapse under its own weight.
Okay, so Jean's mass, I really like that one. And now we're just going to finish with another question, which is a bit more about the kind of observational astronomy. So this question here is about observational astronomy, something which I don't really know much about, but why is this included? Why is this on the test?
So this is an optional question, and this optional question on observational astronomy has been included to encourage more people to learn about observational astronomy. And one of the reasons for that is that at the International Olympiad on Astronomy and Astrophysics, about 25% of the marks come from observational astronomy skills. Choosing to do the observational astronomy question can be beneficial in that a lot of parts of this question are much quicker than some of the other physicsy questions. So by putting more sort of revision and preparation in, you're actually saving time for the other physics questions in the actual exam.
Okay, cool.
That's one of the benefits of doing this question. If you know the stars and constellations off the top of your head, you can do this more quickly than the other questions, I think.
Cool. So should we have a look at some of the questions then?
Yeah.
So what really does a show to like a beginner in this side of things?
I should add, all the resources you might want to self-teach everything you would need to answer this question are in the BAAO Observational Astronomy study guide that's available on the website. And in the syllabus that's also available on the website is a checklist of everything you might possibly need to know. So the syllabus presents a checklist of everything you might need to know for this question. And this study guide right here And this study guide right here kind of walks you through all of those syllabus points and provides some tips and tricks and other kinds of things and explanations.
And you put this together.
Yep.
And so it is really good, actually. So it's really well written. And I think this can go a long way to helping you solve these kind of things. And you can see there's so much information throughout the whole thing. I think it's about 43 pages long. So there's a lot of good stuff there for you to kind of really get your teeth into. So question A.
So if you haven't quite gone through the observational astronomy syllabus yet, and you're maybe thinking of answering this question, some of the things that we're about to say might seem a bit daunting. It might seem like there's a lot of information that kind of I'm just sort of bringing off the top of my head.
Yeah.
I'd say that the first few constellations, stars, Messier objects that you learn will probably seem like they take a while to sink in. But then once you've got that background, once you've got those first few things memorized, everything else becomes increasingly more easy to learn because you're kind of fitting it into a framework of what you already know is there.
Okay.
So once you see a star map, you're going to want to look at it for a little bit and just orientate yourself and just know what's there before you try and sort of say, oh, what's that star?
Okay.
You want to just look at it, and I would highly recommend, if you see a new star map, just draw constellation lines immediately for some of the constellations that you recognize. So one of the most recognizable ones here that I'm seeing is Orion. You can spot Orion by his belt here and these 4 stars here. Again, Orion has quite a few bright stars, and it might be one of those first constellations that you spot. I think I mentioned this in the study guide, that it can be really helpful to kind of make a story out of the constellations to remember what's where. So I see Orion, and I remember that actually Orion has a hunting dog running behind him. And so I look back, and indeed, Canis Major is here.
Yeah. Oh, I see.
Yep. So there's that dog. And I also know that Orion is facing towards a bull. And sure enough, I can see the bull's face here. Again, this seems like I'm just kind of pulling these things out of nowhere and just spotting them, but it is something that you get used to, even if it seems intimidating at first. Okay, so what I'm going to do now is to just draw on the constellations that I recognize, but trust me, like you will also be able to recognize them. Here I can kind of see the shape of Perseus. I kind of think of Perseus as like having these little legs.
Okay, yeah.
Yeah, so he's one of my favorite constellations because you just see these little legs just in the sky.
I think you've got a very vivid imagination, definitely. Yeah.
I think it's good to have if you have a vivid imagination, that's going to come in very handy for learning some constellations and stars, because let's be real, most of them really don't look like what they're supposed to represent.
Do you know what? I'm impressed by the dog, though. Yeah.
Yeah.
So, no, but I think making stories really kind of builds up that
Yeah,
kind of
definitely.
the picture, and it really helps you remember things, doesn't it?
Cassiopeia is a fairly recognizable one because she looks like a W. I mean, someone long ago thought that Cassiopeia looks like a queen.
Yes. Okay. Cool.
Looks like a W.
Yeah.
And the story, again, making a story. So Perseus is rescuing Andromeda, and then they're flying away on a Pegasus. Again, I'm saying all these things. It sounds a bit crazy, like if you haven't really come across these things before. But as I mentioned, either inventing your own stories or reading up on what the actual mythology behind some of these constellations was is surprisingly helpful in remembering where they are, what they look like.
And I think a lot of these words, people recognise them. So people know about Pegasus or Andromeda. There are certain phrases and words that people are familiar with, even if they're not necessarily aware of what they actually look like on the star map.
The document talks you through all of these things. So I think from now I'm going to proceed assuming that you've gone through the document. Also, if you really don't want to answer this optional question, then I think this is the last one that we're going to cover in this video.
It is, yeah.
So you're welcome to not watch the
No, don't say that. Subscribe, and then you can
First,
stop watching the video.
subscribe,
Yeah.
and then you can go on to a different Physics Online video.
Exactly, yeah. Okay, so we've got some of these.
Yeah, so I'm just looking around and seeing what things I can spot. Here, this square here is the Great Square of Pegasus. Also, I should add that a lot of people say like, oh, I wanted to do like physics and maths questions. Why do we have to like do all this like looking at pictures now? But I don't know about anyone else, but I find it kind of a welcome break. So you do lots of physics and maths, and then you also do some of this. The different styles of question kind of complement each other nicely, and you don't really get bored of doing any one kind of thing.
Yeah, and I think there's plenty of other maths within the rest of the paper to kind of keep you satisfied with that.
Yeah, exactly. Cool. I've identified a few constellations, but I've kind of identified the constellations that are near the labels that are probably going to be relevant to the question. So I think what I'm going to do is have a look at the question and then come back and draw on more lines if I need to. So part A, name the stars being pointed at with the arrows labelled A, B and C. I mean, this is kind of a question of do you know them or not, which the guide will talk you through. I might just write them on.
I think so, yes. I think this is the kind of question where your knowledge means that
you either know it or you don't.
And if you know it, then you probably can get 3 marks in about a minute. I guess if you look at that, you can just go, well, that's definitely that star. So yeah, so what are they called, these ones?
Excuse my scribbling. I had a hand typo. Okay, so A is Alpheratz, but by the way, there are 2 different systems for naming stars. One is by the common name, for example, Alpheratz, and the other one is by the Bayer designations. And the Bayer designation is a system of naming stars where you take each constellation, you call the brightest star Alpha, and then that constellation, and then the second brightest is Beta, etc.
Okay.
But I personally find the common names more memorable.
Yeah.
Because remembering Alpha, Beta, that kind of thing, it's kind of the same for each one, each constellation then. But the common names, they're all different, so it's kind of, it becomes more memorable. But I think regardless of whether you write the common names or the Bayer designations, you'll still get the marks. So just learn whichever version works better for you. So star A is Alpheratz, B is Rigel, and C is Aldebaran. Okay, so that was a quick 3 marks of part A.
Yeah.
Now, part B is a bit trickier. I may have implied earlier that this is easier, but it's not really easier, it's kind of just different.
Yeah.
So for example, part B, estimate the altitude of Sirius to the nearest 2 degrees and state the angle marker from the scale around, so here, that it's closest to. And again, the OBS guide available on the website will guide you through the standard method for estimating the altitudes of stars. The altitude of a star is the angle from the horizon to that star, sort of how high it is above the horizon.
Okay.
And there is a method for doing this. If I could just borrow the ruler.
Right, here we go.
Right, how to find the altitude of a star. First, you want to find the center of the star map.
Okay, so that's fairly straightforward.
Yep. If you have the cardinal points and angle markings, then that is fairly straightforward because you draw a line from north to south.
Yeah.
And then you draw a line from east to west. And here is the center.
Okay.
And the reason we're finding the center is because there's an approximation you can do to find angles on a star map. And that is the way the projection of these works, almost all the time, is that if you draw a diameter, then the length along that diameter anywhere will be proportional to the angle across the sky that covers.
Right.
So for example, if you look at the sky and think of the angular distance from here to here, that as a fraction of this length will be the same as the fraction of that angle to 180 degrees.
Okay.
Does that kind of make sense?
Yeah.
Cool. So whenever we measure the altitude of a star, first we find the center, and then we want to draw a diameter that passes through that star. But I'm getting slightly ahead of myself because we need to find the star first.
So again, if you don't know where Sirius is, it's very hard to answer the question. So you need to have that bit of knowledge, don't you, to unlock the rest of the mark.
Yeah. So that said, if you forgot where Sirius was and it showed you're working fully with a different star,
so you
probably would get.
So you could label this one Sirius, and I'm just going to pretend that's the Sirius star, and then you could do the rest of your calculations based on that.
Yeah, the funny thing is, that turns out to be Jupiter and not a star at all, yeah.
Okay, right. I did engineering at university.
Yeah,
this was not part of my course.
But this is spoilers for part D.
Okay, right, okay.
Yeah, but that is fun facts for part D, actually.
Okay, cool.
So Sirius is the brightest star in the night sky. We'll later find that this is not a star.
Okay.
Despite looking brighter than Sirius. Sirius is actually the brightest star, and it's in Canis Major, which is behind Orion here. And the way we're going to find it, I'm going to draw a diameter. Okay.
Yeah.
And again, this isn't all going to be fun and games and labeling on the star map. We're going to have to do some working out as well. So let's get that out. So what we want to do is we want to measure the length of this whole line. That's 20 centimeters.
Yeah.
And the distance from the horizon to Sirius is 2.5 centimeters.
So you're talking about the distance from the edge?
Yeah.
Okay.
So we've measured this length on our A3 sheet of paper, that's 20 centimeters, and this distance is 2.5 centimeters. And because of the way these projections work, again, this is something you kind of, it's something you should know about the way that these star maps are made. In particular, the ones that you would come across in round 1 of the BAO, is that this 2.5 centimeters to Sirius over the 20 centimeters of the diameter is equal to the altitude of Sirius, which I'm going to denote A for altitude, why not, over 180 degrees.
Okay, cool.
And I wouldn't write in numbers before rearranging, so I'm going to denote the distance from the horizon to Sirius is D, the diameter of the whole map is, and we get 22.5 degrees for the altitude of Sirius.
And so we've got the altitude of Sirius to the nearest 2 degrees. And then the angle
to
marker.
the nearest 2 degrees, this would be 22 degrees, not 22.5.
Okay, cool. And then what do you mean by the angle marker that it is closest to?
Oh yeah, so we're seeing these sort of angles labelled around the edge, and looking on this side, drawing the diameter has really helped us to find which one it is, and that's the 100 degrees mark.
Cool.
Okay.
Very nice. Another 2 marks. And I guess, I guess looking at this, that's a lot less work than the kind of getting 5, 6 or 7 marks on that big question about Jean's maths.
Yeah, that said, it was a lot more work for 2 marks than the 3 marks here, because you had to draw some lines, measure some distances, but once you've done a few of these, you'll be able to do them fairly quickly. Just remember to bring a ruler to the exam. So
for part C, we need to name 3 fully visible, so stars above the horizon, zodiacal,
zodiacal, I would say
constellations
zodiacal.
That the galactic equator passes through in this image. Okay, so lots of stuff you have to understand to answer that. So how would you approach this?
So this one's combining knowledge from like different parts of the syllabus, because firstly you need to know which constellations are on the galactic equator.
Okay.
And you also need to know which constellations are the zodiac constellations. Again, it's not easy to sort of remember and like rattle off a list of the ones that are on the galactic equator. From the syllabus, the ones that are on the galactic equator are Orion, Auriga, Perseus, Cassiopeia, Cygnus, Aquila, and Canis Major. But a kind of life hack for finding the galactic equator, if you forget exactly where it is to sort of squint a little bit, take a look at it. And can you see how there's like a band of where there's more stars around here?
Yes.
So there's a lot more bright stars kind of around this region here.
Yeah.
And they seem to be more dim in general around here.
Okay.
And that's just a way to generally know where the galactic equator is.
So I'm thinking if you're outside at night and you see this kind of sort of like the Milky, the bit of the Milky Way, the kind of the white bit that goes across the sky, that's where you're going to be looking at like the equator, or the kind of the flat bit of the galaxy, I guess, isn't it?
Yeah, you're looking kind of into the plane of the galaxy.
Yeah.
But even if you don't see that kind of milky smudge, even so, you'll be able to see that there are more stars. Again, I think, at least not where most people live, you'll be able to see like enough stars to really tell where the Milky Way is. But on a star map, you can kind of see how the density of stars is kind of increased around. So, you know, suppose we've forgotten where the galactic equator is. We know that these constellations here are probably going to be on it.
Yeah.
And so we have a look at this. And we say, well, Orion's on the galactic equator. And we can see that we've got Canis Major, Orion, Taurus, and Perseus that kind of seem to be on that line there. However, they wanted 3 fully visible non-zodiacal constellations. Keyword here is now non-zodiacal. Taurus is a zodiac constellation. These are the zodiac constellations.
So I've got this from the guide, and you know, you can see that this is Taurus up here, which is up there. obviously different angles and everything. Oh, sorry. Yeah, so it's like a different angle. But it's interesting to kind of remind yourself of not only the names, which I think a lot of people are familiar with.
Yeah.
Do you believe in astrology?
No.
So this is a bit of astrology, is it?
That's not astrology.
Okay, right, okay.
Astrology is a banned topic.
Okay, but then here we have some shapes.
It's a safe space. We can see, so these four are on the galactic equator. However, Taurus is a zodiac constellation. So my answer for this is going to be Orion, Perseus, and Canis Major.
How do you know they're above the horizon?
I mean, I can kind of see their shapes fully here.
Yeah.
The ones below the horizon, well, are the ones that you can't see.
Fair
so
enough.
by
Cool.
looking at the things that you can see, this question says fully above the horizon. So technically you could say Cassiopeia or Auriga, but because they're so close to the horizon,
Yeah.
it's kind of risky. You don't know whether they technically count as fully being above the horizon.
Cool. Okay, very good.
Part
So
D.
now we've got something about some planets. So Jupiter
Yeah.
and Saturn. So you've already told me that's Jupiter, but is that Saturn?
That's actually the moon. This one's Saturn.
Okay, there we go. So again, a bit of knowledge will definitely help you. You can't just guess it. So okay, so how do you know that they are planets and not stars?
Yeah, so there's a section in the OBS guide that goes through how to find planets on a star map. Planets are going to be near the ecliptic line. And the ecliptic is kind of that line on the sky where the sun and the planets and like other things in the solar system all move along throughout the year. And the zodiac constellations are the constellations that the ecliptic passes through. So in other words, you could say, when you're looking for planets on a star map, you know that they're going to be kind of near where the zodiac constellations are. The zodiac constellations are the constellations that the sun passes through over the course of the year. And then the planets kind of move in the same plane as that.
Yeah, that makes sense.
Yeah. Another thing that's outlined in the OBS guide that will be helpful for this question is that, crudely speaking, the only two things, or at least the only two stars as such, brighter than Sirius, which is right here, can be Jupiter or Venus.
Okay.
So here they've said Jupiter and Saturn are both visible in this image. They've not mentioned Venus, so we probably don't really care about Venus right now. Probably it's not visible. And it says, name the two nearest zodiacal constellations to Jupiter. So we want to find Jupiter. And what we're looking for is an extra star, it's near the ecliptic, and it's brighter than Sirius.
Okay.
And scanning through to find something brighter than Sirius, I found this one here.
Should we circle that?
Yeah,
so
that
don't
must be
forget?
Jupiter. So that's Jupiter right there. And from there, we want to find the two nearest zodiacal constellations. So Taurus is a fairly recognizable one.
Yeah.
We kind of drawn those lines for Taurus earlier. However, what about the other one? Because it's not immediately obvious what other zodiac constellations are here. And I think the quickest way to sort of figure out what the other one is to recall the order of the zodiac constellations in your head. Because you know that whatever else Jupiter's going to be nearest to is going to be one of the ones that's next to Taurus.
Okay, so basically the sun passes through these constellations throughout the year, and the order is important, and you need to know that.
Yeah, it's definitely worth knowing the order of the zodiac constellations. And again, although astrology is a banned topic here, if you use remembering your friends' birthdays to remember the order, then so be it. Remember the order however you wish.
Yeah.
So we know that Taurus is next to Aries and Gemini. And from seeing quite a few star maps before, I know that I'm expecting Aries to be here.
Oh, yeah.
Here's Aries. That looks quite a lot like there.
Yeah.
And that Gemini is going to be around here. So from remembering the order, I kind of knew which constellations I wanted to look for. And so the answer to this one is that it's Taurus and Aries. Okay, moving swiftly onwards.
Okay, so actually, it's all right at the moment, isn't it?
Yeah.
Okay.
Again,
The moon.
if you remember the stuff.
If you remember the stuff, it's easy. If you haven't remembered it, it's very hard to
If
guess.
you haven't remembered it, just do the other
Do
If
the
you
other
haven't remembered
questions.
it, just do the physics questions.
Yeah. So the next one, the moon is indicated as a grey circle in the west, which is over here. Which zodiacal constellation is it in?
Yeah, so a translation of this question is kind of like, here, what zodiac constellation is here?
That's all it is, yeah.
The moon's just an indicator. And again, this is quite a dim patch of sky, but from kind of what I'm currently remembering is that I know Pisces is kind of under here because I use Pegasus as kind of a reference.
Okay.
And I know that under Andromeda and Pegasus here, I know that Pisces is around here, Aquarius is around here. Again, this seems so vague.
Yeah.
This seems so vague, but I know that Pisces is around here. Again,
Oh yeah.
I
So
often
see.
can't draw the exact lines. And then Aquarius, I remember, is around here.
Yeah.
And then moving on, I can just, even though it's quite dim, I can just vaguely pick out Capricornus here. And so the answer to this one is Capricornus. Again, it's a case of remembering where things are, but lots of tips and tricks for that are in the OBS guide. Part F. Trust me, part G will be a bit more involved.
Okay.
For now, there's lots of recalling information, but part G will be a bit more kind of problem solving-y.
Cool.
So part F.
So you've got these, I can't pronounce it, Messier.
I think that's fine, like
Sorry,
Messier.
Messier sounds better. French astronomer, astrologer. Okay.
No.
So we've got these objects here, M1, M31, M42, M45, M57, M76. And again, some of these numbers seem familiar from like the first part with the Astro Challenge. So I guess there's a few more that you need to know for this paper.
Yeah, whilst there are 4 Messier objects that you need to know for the Astro Challenge, there's a bit more that you need to learn for the round 1.
Yeah. So for each of them, state if they are above or below the horizon in this image.
Well, the first thing to do would be to find them. And again, one of the nice things about these questions is that if you do forget a few things, you can just guess. Considering there's a 50% chance of getting it right,
That's true.
you can guess if it comes down to it. I know that M1 is around here. I know that M31 is the Andromeda Galaxy.
Okay.
Oh, there's a crossover. That's strange.
Yeah.
M42 is the Orion Nebula, which is here. So far, they've all been above the horizon. M45 is the Pleiades here. Again, there's lots of tricks I have for remembering these things. For example, M1 is a crab nebula, and it's kind of on the tip of Taurus's horn. So it's like, oh, just like that's like a crab on the tip of his horn. Like, just like that little sentence, it just kind of, you just can't forget it.
And you build a picture and you build a bit of a story, and I guess it just builds the more you do, isn't it? Okay. So
and M45, the Pleiades, are in the bull's stomach, because why not?
Yeah.
And then M57, well, that's the Ring Nebula, and that's in the constellation Lyra. But I can't really see Lyra here. So, okay, maybe that one's below the horizon. M76, I have a hack for this, actually. So Andromeda has these 2 bends right here, yes?
Yeah.
The larger one bends towards M31, and the smaller one bends towards M76. This could be kind of slightly off to where it genuinely is, but I know it's kind of in this region here.
Okay. So just going through that, we've identified M1, M31, M42, M45 and M76 are all above the horizon. And also the cross is Andromeda.
Yes.
That you've identified, again, just from the knowledge that you've got that I don't have yet. But I'm going to start learning this. This is interesting, actually.
It's quite fun because, again, the first few things that you learn will seem to take a while and it'll seem quite intimidating. But you quickly get to the point where you're kind of just adding things to an existing set of knowledge rather than just learning that skill for the first time.
Cool.
Give the name and Messier number of the deep sky object whose location is indicated with a cross. So we know that it's M31. What's the name? The name is the Andromeda Galaxy. Clue is that it's near Andromeda. It's just one of those things that you learn. And finally, part G.
Part G.
This one gets a bit spicy. So we want to know which constellation culminated 3 hours ago. And we know that there's 12 zodiac constellations in kind of a 24-hour day. We know that in a 24-hour day, the Earth is going to rotate 24 hours, and there's going to be 12 zodiac constellations like passing through the meridian over the course of the day.
Yeah.
So let's make a crude approximation and say each zodiac constellation is on average going to take 2 hours to pass across the meridian.
Yeah.
Right? Some of them are huge, like Pisces. So this approximation is crude. But for the purposes of doing this question, an approximation like that would be suitable, as long as you explain it well. This is just one of the ways you could have attempted this. There are more accurate ways that you can do this, but this is just the method that I'm going to explain now. So approximating, so it takes approximately 2 hours for each one to pass, which means that 3 hours ago, that's kind of 1.5 zodiac constellations ago, if that makes sense.
Yeah.
So currently we're on Aries, and as we mentioned before, here we've got Pisces and Aquarius. So if we kind of move back 1.5 constellations, we end up with Aquarius being the one that culminated at midnight, right?
Okay,
So if we move everything that way by 3 hours, going 1.5 constellations along gives us Aquarius. Slightly more because it's 3:19, not 3 a.m.
Okay.
One of the many reasons to remember what the zodiac constellations are in order is so that you can count along 6 zodiac constellations from Aquarius.
And that's where the sun would have been 12 hours ago.
No, that is where the sun currently is.
Okay, sorry.
So the sun moves through the zodiac constellations over the course of the year.
Okay,
Just to clarify, all the zodiac constellations will cross the meridian over the course of a 24-hour day because the Earth rotates once per 24-hour day. Over each day, all the zodiac constellations will cross the meridian, but only once per year will the sun move through all 12 zodiac constellations.
Okay.
So, and we, in order to find the time of year, we want to know which zodiac constellation the sun is in right now. We know that since Aquarius culminated at midnight, Aquarius was at its highest at midnight. This means that the sun is directly opposite Aquarius.
Okay.
Because if you think about it, midnight, where midnight occurs on the sky is kind of opposite where midday occurs.
Yeah.
Right? At midnight, wherever your observer is facing in the opposite direction to where the sun is. So we know that Aquarius culminated at midnight, and counting along 6 to find the zodiac constellation that's directly opposite Aquarius. So we go Aquarius, Pisces, Aries, Taurus, Gemini, Cancer, Leo. We count along again. If
I don't know my star signs.
What I would do is write out all 12.
So we're looking at Aquarius.
Yeah, so counting along, we've got Pisces. It doesn't matter which direction you count in, it's 6 hours anyway.
Yeah.
So 1, 2, 3, 4, 5, 6. So the sun is in Leo right now. Because when it's midnight, we're facing directly towards Aquarius, that means that at midday, we must be facing directly towards Leo. And because that's midday, that's where the sun is too.
Okay. So the sun is in Leo. And how does that tell us which month we're in that case? So
the sun being in each zodiac constellation corresponds to a specific month. This is an approximation. Of course, the zodiac constellations don't align specifically with specific months.
Okay.
The end of July, it does kind of overlap into Leo as well.
Oh, I see.
But for the purposes of BAO round 1, we associate each zodiac constellation with a month because, again, the purpose of all of this is to kind of encourage that way of thinking and get you to solve those kinds of problems. And approximations like that, you can always correct for them later on when you do more difficult problems later on.
And so just by knowing which part of the zodiac the sun is in, that just tells you exactly the month. And
Yes.
it's just a fact that you can remember. So as long as you know one of them, you can just sort of count on 12 or count on however many star signs and months.
So if the sun is in Leo, then the month is more or less August. This map is actually taken from kind of near the end of August, but the reason we haven't got exactly the right answer is because we've done quite a vague method.
Yeah.
We've approximated it. But to get full credit, you'd need to sort of write out your thinking. Again, when in doubt, write more, not less.
But I think it's very clear how you've gone through that approach. So you've looked at where it was 3 hours ago. Then I guess we've got the opposite to that. And then if we know it's in Leo, then we can then associate that with August. And there we go. That was the end of that question. So that question 6, a lot of new knowledge, especially if you haven't done GCSE astronomy or you've maybe only been doing, or say only, but only be doing A-level physics. But actually, there's a lot of stuff there that you can self-teach. And I think actually, if you know that stuff, you can probably work through this question a lot quicker than some of the mathematical ones.
Yeah. The preparation that you put into memorizing these things will eventually save you time in the exam. So you can then allow yourself to spend more time on the other physicsy questions.
Fantastic. Well, thank you so much for your help today.
Thank you so much for having me here. It's been so fun.
Yeah, and of course, if you'd like to find out more, I think the BPHO website, it's got the past papers, it's got work solutions, it's got your guide of how to actually learn astronomy and do a bit of self-guiding and stuff. But thanks a lot for all of your help today. Really appreciate it. Thank you.